see, every human on the planet has been able to see this star cluster. It's 80 million years old, and it's right on the equator, so it's almost straight overhead here in Indonesia. And you can see it where I grew up in Alaska, and you can see it down in the southern part of Patagonia. And this star cluster and the story of the Seven Sisters is used in Australia to do a map of how to move around the continent from place to place and do things through the seasonal cycles. But it's a story that quite remarkably is seen around the world. It is the Pleiades story. It's the same story in Greece. It is in India. It's in Thailand. It is all over the world. It is, as near as I can tell, a story that is probably more than 50,000 years old because it is shared amongst the world's peoples. And just to give you a sense of how old astronomy is, this is the Lascaux cave in France, very famous picture of the bull. And if you look there are the Pleiades. And why are they there? Well, it turns out that's Taurus the bull. The constellation Taurus is where Pleiades are, and it is depicted back 17,300 years ago that. So these stories of astronomy are ancient. So astronomy, of course, connects into the modern world, I think largely through the Greeks, who started trying to calculate where the planets went. And Ptolemy went through and created a very complicated, in one sense, very simple idea, essentially by saying the Earth is at the center. Why? Because he was going to be killed if he said anything else. Objects travel in circles. Why? Because he was going to be killed if he said anything else. And his job was then to figure out how to predict what those two basic tenets, how the planets work. And it turns out you can, by adding lots and lots of circles and having good data, terrible model, but a good enough model, you could actually predict where the planets were. And this turned out to be the best way to predict where the planets were until the 1600s. All right? Now, it started being challenged in the 1400s when Copernicus came along and said, wouldn't it be so much conceptually simpler if we just threw away the idea of the Earth being the center and we put the sun at the center? And it turns out if you do that, you could predict most of the motions of the planets. Now, he only had circles with the Earth at the center, or the sun at the center, so he couldn't do as well as Ptolemy did, because Ptolemy had so many circles, he could fit the data. That's what we call modern parlance overfitting, but he did it. But it changed the concept, because you could go out and you could actually test, it turns out, in the next 100 years, whether or not Copernicus was right. And this came from making and taking data really accurately. So Tycho Brahe went through and built instruments, scientific instruments, that turned out to be useful for measuring the position of Earth really accurately, but they were really good at tracing where the planets went to an order of magnitude more precision than ever before. And that allowed Kepler, who worked with him, to go through and to deduce, for example, first of all, that orbits were ellipses. It allowed the laws of motion to be developed, and it eventually, he also had crazy ideas, it turned out, about things fitting in spheres of different sizes that were nonsense, because the scientific method was not really developed. You had ideas which you essentially said were correct, and you went from them. And it was really Galileo who went through and put on the modern idea of testing things. And so he was very famous for creating telescopes that could look at the stars, and actually sold them to the military people of the time. That's how he funded himself along with some students. By all accounts, he was a pretty terrible teacher, so it was better to sell his telescopes than teach. But when he looked at, for example, Jupiter, he could see moons, and you could see that the Earth was not the center of that system. He could see the phases of Venus, and under Copernicus's model, When Venus was a long ways away, it would be small and full, and it would be a crescent if it were close when it comes on the other side. Exactly what Copernicus said, and not what Ptolemy said. So that was that ability to go through and test things. Galileo did it here, then he applied it to gravity and all sorts of stuff. It was the beginning of the scientific method, really improved dramatically by Newton, who then built up a mathematical framework to go through and be able to predict things through calculus, and putting out the theory of gravity, and that is essentially the beginning of the scientific revolution, from which the incredible technological advancements of humanity come from. And it comes from astronomy every stop on the way. So an amazing beginning to the scientific method. It continued in interesting ways. So we started building telescopes to get more data. And those, very soon after the big ones were built, discovered a new planet, Uranus, that was not known. And you could go through and you could use Newton's laws to look at its orbit, and it didn't work. So maybe Newton's laws were wrong, or maybe there was another planet. So it turned out if there was a planet Neptune, it would perturb, by Newton's laws, Uranus's orbit. They went out and almost immediately after it was predicted, and they discovered Neptune straight out of bed by using science. Scientific method, you predict things, you test those predictions, and when they're right, you kind of know you're doing something good. It is a philosophy that is very powerful, and it is having ideas that you test. Never assume you're right, you always assume you're wrong, but you keep predicting things. And as long as you're pretty confident that you can predict what you see, then you say that's a good enough model of the universe, whether it be building an airplane or extracting nickel successfully from a mine. It is that process, that scientific process. So it turned out that in 1907 we had an aberration to this model when Albert Einstein had an idea that acceleration due to gravity and acceleration due to moving faster were effectively the same thing. That is, you couldn't tell if you were in a rocket ship or you're just sitting on planet Earth in a box. They are the same thing. And that turned out to be really hard to reconcile with the laws of physics, but he spent 8 years doing it and ended up coming up with his theory of gravity, general relativity, which predicted that space is curved and that all these things that we assume to be true with Newton's laws were close to being correct, but not exactly correct. There could be things like black holes, there could be, as I said, the curvature of space, there could be gravitational waves. And so it turned out when we went out and we looked at this idea, which Einstein really came at from thought itself. I mean, he came out with thought itself. It turned out he was right. And kind of along with Copernicus, where someone says, I have an idea, it must be right, and everything changes, that's really only happened twice as near as I can tell in all of humanity. Normally, you do things because when you predict, you don't get the right answer. When you don't get the right answer, then you know there's something wrong, you start changing your models. That's the way science normally works. So, Einstein, and telescopes vindicated Einstein's theory of gravity, and it was done through pictures of an eclipse. You looked at the stars behind the sun during an eclipse, you could see them, then you waited 3 months, the sun was gone, you looked where their stars are, and bent space, if space is curved, then it turns out it distorts where the stars appear in the sky. And it got exactly the correct answer. This, interestingly enough, is what made Einstein famous. Einstein was famous to physicists after 1905, but this is what put Einstein on the front pages of the newspapers, because he literally came up with a profound change of our understanding of gravity, Newton's laws, from pure thought and aesthetics alone. It wasn't E equals mc squared that made the household. So astronomy is really the essence of science. It helped, as I have indicated, develop the scientific philosophy. A theory, an idea is created, it is fit against what you know and see in the universe, so the theory predicts things, you compare it, and then you either keep your ideas in place, or you have to modify them. And it's that circular motion that is the power of science. And so when people say, you know, science gives you the facts, science doesn't give you the facts. Science makes predictions. And predictions are way more powerful, really, than facts. Because when facts are wrong, people lose trust. People need to understand this is a cycle of improvement. And it's why scientists are not obviously ever going to lose their jobs. Because we're always improving what we know and what we can predict, and therefore what we can do with the knowledge. So in that sense, some job security. So let's take this to me. I grew up in the middle of nowhere in the state of Montana in the United States, up in the mountains. My parents had me very young, but they were at university, and here I am with my dad up in those mountains at the age of 5. And I was a pretty normal kid, but from pretty humble backgrounds. Because Montana was not remote enough, my father, who was a biologist, moved us to Alaska, and here I am with a telescope out in Alaska. And one of the problems with having telescopes in Alaska is that during the summer, it never gets dark, and in the winter, it is so cold that it is really hard to get your telescope out and work, because when it's 40 below, it's 40 below. So here I am with my telescope taking pictures of dull sheep in the near Mount McKinley in the Alaska things. But I'm 15-year-old. So I guess what I want to tell everyone is I was not predetermined to be a Nobel Prize winner. I came out of it as a normal kid from a normal place, from a normal family. So that is the beautiful thing of how science works. It does not care where you were born, and who your parents were. It actually cares about what you get along and do. So I think that's good. And you'll hear next from Jagadish. And I come from very upward surroundings compared to Jagadish, who came from, I had power in my house. I had to chop wood to stay warm. So we had wood-fired stoves to stay warm, but I didn't have power. And Jagadish did not even have power. So, astronomy, and I'm a cosmologist. And so, in 1929, Edwin Hubble made this diagram. He compared how bright a star was, and the further away a star is, the fainter it's going to appear. And so, using a law that Newton created, inverse square law, you can estimate the distance by how bright a star, the same type of star is back in time. And so, he went out and he literally measured the distances to a bunch of galaxies of stars. And then another person using a telescope had looked at these galaxies and realized that the galaxies, using the same technology we would use to measure, for example, your speed on a highway to make sure you're not speeding, the Doppler effect, had measured essentially how red the light was coming from this galaxy, and saw that it was shifting a little bit, and then he could measure the velocity using the Doppler shift. And so the Hubble in 1929 plotted the redshift, which is on the y-axis, so how fast the galaxy is moving away by its redshift, the Doppler shift, and how far away it was by how bright its stars was. And you can see there's a correlation. The further something is away, the faster it's moving away. And from that, he announced to the world that the universe is expanding. So why did he say that? Well, here's a cartoon. So I've got the universe, and I'm going to expand it. So see, I've just expanded the universe in my cartoon. Let's compare before and after. Well, if you compare before and after, you can see that nearby objects, when I expand the universe, move a little bit when I expand it, and distant objects, well, they move a lot. The further away something is, the faster it appears to move. So the cartoon really gives you the right answer. Well, it turns out Einstein's theory also predicts this, even though Einstein didn't realize it at first. But before we get there, let's just do a thought process. Imagine the universe is expanding. Now, let's think what was happening in the past. Well, if I look back in the past, that means the universe is smaller and smaller and smaller, and at some point, everything in the universe is going to be on top of everything else, and you naturally get the idea of a Big Bang. The universe is expanding, you get a Big Bang. So, the theory of general relativity allows you to essentially look at how the universe expands over time. It's actually very simple, relatively speaking. So, if the universe has no gravity, which is the simplest idea, the universe is expanding, it just keeps expanding. And so the separation of galaxies just grows over time as a linear function. So that dotted line turns out to be the distance of the galaxy divided by its Doppler shift, its velocity. So if I measure d over v, which is what Hubble did, I can run the universe back in reverse, and I can figure out how old it is. I can measure how old the universe is. And that is what I did for my PhD thesis. I used exploding stars called supernovae at Harvard, and here I am in 1993, 3 years, 11 months, and 4 days after I started, but I wasn't counting, showing my PhD supervisor how fast the universe was expanding. And how fast was the universe expanding? Well, such that the universe was about 14 billion years old. All right, so now I said that's assuming there's no gravity in the universe, but general relativity says, well, there can be stuff in the universe, and it changes the trajectory of the universe, and you can calculate it, but it's not dissimilar to throwing something up here at Earth. When you throw it up, it slows down, and so you can kind of calculate things like you would on Earth. So the universe might be a little younger than that 14 billion years old if the universe has a lot of stuff in it. So that's something to be concerned about, and it's quite profound for the future of the universe, because if the universe isn't slowing down at all, obviously it just keeps getting bigger and bigger. But if it is slowing down a lot, then the universe will stop expanding, and just like a ball I throw in this room, with less than the escape velocity of the Earth, it will reach a maximum height and then fall back. The universe reaches a maximum size, stops, and then goes in reverse. So all universes start with a Big Bang, but only the heavy ones end with the get out give, the Big Bang. So I moved to Australia in 1994, as indicated, by pitching the idea that I could use new technology to go back in time and look at really, really distant objects, supernovae, and I could measure d divided by v, not just now, but billions of years in the past. And I could do that because of new technology. And that new technology, as I'll show you, based actually on astronomers inventing stuff and becoming useful, and then you get a beautiful virtuous cycle, which we talked a little bit about earlier. So the idea is, if the universe is slowing down faster than that dotted line, then gravity is going to win. The universe is going to eventually stop expanding and then start contracting. So the universe is finite in time, and if it's on the other side of that line, then it turns out gravity loses, and you've effectively got escape velocity, and the universe just keeps getting bigger and bigger forever and ever, and the universe has no end. So a profound idea. So it turns out we could do this thanks to my colleagues learning how thermonuclear detonations in space, and yes, my colleagues work on nuclear bombs as well, not maybe the good side of the job, but these things take about 20 days, they're 5 billion times brighter than our sun, they fade away, they create most of the iron and nickel in the universe, so When you mine nickel in Indonesia, it came from these things. These are the things that produce that nickel in the universe. I will not charge you a royalty unless you'd like to provide one. We'd be more than happy to do so. Okay, now the technology we had to do is we had digital cameras. So astronomers were in the middle of inventing digital cameras. They were sort of created by people working in astronomy for defense. Defense declassified them. Astronomers went nuts and actually helped build the technology out such that by 1994, we had 8 megapixel cameras, digital cameras, already in 1994. So well before there was a consumer market. And we had access to those things, and those allowed us, because they were 100 times more sensitive than film, to look back 8 billion years into the past. And we could find these exploding stars, which are really faint and really rare, but this new technology gave us the ability to find and measure how far away they are and how much their velocities are. And so I had to write the software to do all this, to discover needles and haystacks, because we would take about 1,500 images of these a night, and we would find 3 or 4 objects each night. And I used early versions of AI to do this. We had to do all sorts of image manipulation, and it shows here an object that we had observed, and then we came back a few weeks later, and you can see nothing here has turned into something. That object, 5 billion light years away, meaning its light has taken 5 billion years to reach us, which means it exploded before the Earth was formed 4.54 billion years ago. So you really can look back in ways to before even the Earth was formed. This took a lot of effort, a lot of time, and involved a lot of people. And let me take you to Chile, where a lot of the work was done, and Hawaii. This is the instrument. It's run largely by the United States, but it's Australian. I'm in Australia now. I could work with my American colleagues, so collaboration is really important. And so we only get 6 nights a year. And that's the most time anyone gets on these telescopes, because they're very precious resource shared by everyone. So we have to make sure everything is right. So the data comes through, and then my software, which is running on every computer available at the observatory, because it uses a lot of bandwidth, is popping up candidates. And then we have a veritable sweatshop of astronomers peering through using our AI, because the AI was not that good, to say that's an object, that's not an object. We get together, and we have to then get a redshift, that is velocity, using the largest telescope in the world in Hawaii. And so that is pre-scheduled in advance, 36 hours after we take the data. So this all has to happen in 36 hours. And with this telescope, we're able to look at those objects, make sure that they're a supernova, and to measure their velocity. And there we have Adam Rees, who I won the Nobel Prize with, along with Alex Williams. So an intense journey that after 3 years produced a result that when Adam and I first looked at it, confused us. Because here's the experiment we're expecting, and here's the data. Each supernova is an object with uncertainty, and you can see that the nearby objects and the distant objects, they're offset from each other, but not the way we were expecting. We were expecting those objects on the right to be in either the yellow or the kind of whatever color that is, cyan. I'm colorblind, so I think it's cyan, but it's whatever, that's the bottom one. Instead, every single object is above the line. And collectively, we're 99.95% sure that those objects are above the line statistically. That is, the universe was expanding slower in the past and hadn't slowed down at all, and sped up. Well, that's crazy. Well, so crazy that we convinced ourselves, after a lot of work, we hadn't made a horrible mistake. And at the same time, a competing team at Berkeley, with people around the world as well, got the same answer. So we kind of arrived to it independently, which is one of the important parts about science. It's not usually just one person, it's lots of people looking at things simultaneously. And it's for that that we won the Nobel Prize. And here's the group, a very male group back in 1995. If you're a woman, it's all right. 40% of astronomy is now women. 5% of astronomy was women back when I was graduate. So it's completely changed. All right, and it's a much better field for it. So let's get, and I think the Vice Minister talked a bit about this, but at this point in my talk in Australia, the minister, who is not a practicing scientist, will say, Brian, that is so cool. Why do we pay you to do this? And I can say, because it's there, like Mount Everest, curiosity, it's beautiful, it's part of humanity's culture, for our entire time and species, all these things are true. National pride, that turns out to get a lot of ministers excited. But ultimately it's because it's useful. And useful means it creates economic and other things that the minister ultimately gets elected to provide. And here is an example I want to take. So my field, which is the universe and the physics of understanding the universe in its most foundational way, we call astroparticle physics. One could argue the most useless, out-of-touch piece of science one can do. And it genuinely has no direct benefit anymore. Well, except for sort of this. So, on your iPhone, the Wi-Fi. Well, my Australian radio colleagues helped invent the Wi-Fi standard that we all use by using the technology that they developed to look for evaporating black holes in the middle of the galaxy. Not intended, but that's where it came from. GPS, well, GPS uses precision clocks that physicists developed to make precise measurements, which they learned how to put into space and then use general relativity. It's like the one place we use general relativity in everyday life, because if you don't use general relativity, you're not where you are on the globe. And so GPS, the CMOS camera, actually the CMOS technology that we all have in our pockets on our phone, that is from a mission to Jupiter, developed specifically for astronomers. Now literally $1 trillion market. The World Wide Web created at CERN. Why? Because they needed to collaborate. They were able to think outside the box and stuff. The touchscreen also developed at CERN. If you look at the iPhone, at all of the basic work that went into it, it is an amazing list of things that create the technology that allowed the iPhone to go. Right? It is literally hundreds upon hundreds of inventions done around the world, going right back to where you can trace it. That is how science works. It is not, deliver me a new gadget. It's just not how it works. The gadgets emerge, and you need to have ways of taking knowledge and then getting it to those gadgets, and that is really important. But you cannot just say, build me something, and expect it to happen without that basic work. So, in economics terms, it is spillovers. It's not direct. It's cascading spillovers. And you need, as the Vice Minister talked about, a scientific ecosystem. And it needs to interact with a business ecosystem. Because most scientific discoveries do not directly translate to the economy. The accelerated universe is not directly going to give you economic activity. It does excite children to study science and stuff, so it is part of the answer. It's not direct. It also creates, as I'll show you, a bunch of graduates who go on to do things. Most scientists and their students are often, well, I would say scientists and students often are able to translate uses of this knowledge with companies that employ them or startups that they form. But I should say most students and scientists don't. But that's the way it usually occurs. So probably only 1 in 20 scientists and students are going to create a startup or make some amazing translation. But that 5% is what revolutionizes the world. And by trying to shortcut that 5% and say everything has to go that, you're actually meaning we're not going to do anything because we don't take the risk. We do everything is safe. And you end up actually breaking the cycle of innovation by thinking you can do it in advance. Success, in my opinion, is not forcing scientists to always find translation, but rather making it frictionless so that when you have an idea, you don't have to give away your house or give away your career as a scientist to make it happen. And so you need a scientific research ecosystem that allows people, like me, if I suddenly have an idea, to go do it for a year and then come back to university without paying. So a research ecosystem, and this is echoing what we've already heard earlier, you need researchers with access to appropriate infrastructure, global networks, PhD students, and time. Time to make discoveries at the leading edge. That's what you need. Money, well, money is actually translates into people's time and research infrastructure. I used, in my Nobel Prize discovery, $8,000 Australian was the entire research budget I had. That was it. $8,000. Those are airfares to Chile. That's what we used. Everything else was my time. Okay? Within universities and research institutes, you want things to be frictionless for staff and students to take ideas to existing companies or to start new ones. If you have complex IP agreements to make sure that every university or every research institute gets their maximum amount, then you just end up with nothing, right? So you want the ideas out, and you want to collect tax on them. You don't want to kill them before they're born, which is something that many research institutes around the world do. They kill ideas by trying to make sure they don't lose IP. Stanford does not Stanford because of the IP royalties it collects. It's Stanford because it made many, many people trillions of dollars, and they give back $1 in 1,000, and that's enough. The availability, and I think we heard this, well, I should say, really important for universities, research institutes, and companies to be co-located and working together. This is a place, in Australia we need to work on it, and I think in Indonesia you need to work on it. I think there's a fair bit of distance between the universities, research institutes, and the companies. So really thinking about getting concentrations of people in areas. That's where things bloom the world over. And it's got to be all three of those. Can't just be two of them. You gotta have business there, because the ideas of business are not, I need something, here it is. It's actually fermenting ideas and creating new ideas and year-long, multi-year ideas of how to create value for the company. Availability of capital is really important. And you've got to have expertise about how to manage that capital. Just throwing money doesn't work. You've got to know when to put money in, know when to stop, know when to scale, know when to kill. You want economic incentives for research within existing companies. One of the problems we have in Australia is it's really hard to convince companies to invest in research. They find it easier just to grab research from other places. But that means your productivity slowly fades over time as you become a follower rather than a producer. And government focusing on fixing market failures rather than picking winners. Now, I say that specifically in a variety as an autonomous husband, but government can do things that makes sense. Procurement as a tool to get innovative things into their own pipeline. We saw, military, public health, there's all sorts of places. And then there's the idea of national missions. You've got these missions, and having experts go through and drive activity from university to industry as a mission. Mariana Mazzucato talks a lot about that. That is a great place for Indonesia to help develop both its research and technology, but its prosperity, because you're doing things that it is. Stability is paramount. Research is a 10-year plus thing. When I first arrived in Australia in 1994, Australia and Singapore, Australia was a much substantially more advanced technology than Singapore. Singapore has just stuck and invested in research and technology without blinking for the entire 30 years I've lived in Australia. I am now the chair of their academic research council. I invest in Costa, for example, Costa Nacional. I was the person who was the chair of the committee that made the decision to invest in them, right? It is paying dividends in Singapore now because they stuck with it for 40 years. Singapore has 25% higher GDP per capita than Australia does. And it is an example of good policy going for a long time. And if you talk to the Singaporeans, they'll complain about the lack of business and universities working with them. They have literally the highest GDP in the world with no natural resources. Okay? It can still be better, but it's pretty damn good right now. Okay? So let me finish up and just think about some of the other bits. A really exciting thing that's happened since I won the Nobel Prize, and something I've worked a little bit on, was being able to use the prediction of Einstein that there's gravitational waves when, for example, two black holes merge. And we have reasons to believe black holes should merge. And in 2015, we made a discovery with giant lasers, of which ANU physicists helped build this piece of kit that made this discovery and led to a Nobel Prize in physics. And we have, the universe is full of black holes, and we don't understand why. But I want to use this as something I'm involved with that has created a huge amount of actual translation at ANU. So my first connection was this company called Tessis Labs. It was sort of in cyber cryptography before that was anyone else thought in school. It's kind of gone along and continued to grow. But talking to the physicist from ANU who started this company, I realized that the university was making it hard for him to actually build this company by having crazy IP agreements, which meant no one would invest in it. So when I became vice chancellor of the university, I decided to make a learning commitment to change the way the university makes it much more frictionless for our staff and our students to go out and start companies. And we increased the rate of startups by a factor of 10 by going from IP, the standard Australian model, to let's just invest in getting the ideas out and hoping that things are happening. So this company, Vive Photonics, which was then bought by Nomad, well, when they went and got bought out, here's the PhD student. The week he finished his PhD, we're not quite sure, but we think he got a $6 million check on his graduation week. As this company was bought out and now growing as a very large Australian firm, doing essentially using quantum for making very precise measurements of where you are. And this company, which I've been involved in helping get spun out, and now I'm on its board, used, and I should say all of these companies were in the group that made the instrument that detected the gravitational waves. That's what they did. So it's stuck to that astronomy. This company, Liquid Instruments, uses essentially that same technology to build new age measurement test equipment. So it's an oscilloscope that is essentially software driven, can be reconfigured on the fly. Instead of having a whole rack of equipment, you can do it in one little box. So this is a company that is set to sell $20 million worth of equipment this year. I'm on the board, but it includes 2 ANU physicists as the founders, and a whole bunch of people from Silicon Valley. It's based in Canberra and in Melbourne, and it's creating the products in Melbourne. So these are the types of things that come from this crazy piece of astronomy, just one group that I'm involved in. I've had 11 PhD students. I did run a university for 8 years, so it's a mess. But let's just, about a third of my students are astronomers. But I have science teachers, they're a very important part. Public servants who help make sure the government does the right things. Business executives. I have a couple students who started their own companies. And one of my students was at a startup in the US whose valuation peaked at $10 billion. And she is now an angel investor. And I don't know how much she's worth, but she is worth a lot of money. You know, many, many, many millions of dollars. And that's just my 11. Multiply that by the 1,500 other faculty members at AAU, and you see you get interested. And Nobel Prizes don't allow you to translate things any better than anything is a bit of an error. Jagadish has all sorts of students, done all sorts of stuff as well. So it does actually add up, research and research. It is an exciting time to be doing science. Science and technology are now completely interdependent. And as the Vice Minister said, Indonesia's future growth depends on it building this ecosystem. If you want to boost your productivity, it's going to come from your people. And you've got a lot of natural resources, but you've got to boost your productivity. And that comes from really going through and getting people highly educated and lots of cutting-edge research. So in research, excellence first, scale second. Let me say, not on this thing. In education, scale is everything. You got to get everyone educated, no one left behind, and then start getting the research of the excellence that you go. Research, you really want to be excellent first, scale second, education, kind of the other way. And as you've seen, your neighbors, Singapore and Australia, could be excellent partners, but we need to make sure the partnership is one that has feedback loops that grows so that Indonesia grows and becomes like Australia and Singapore. And at some point, you've got your own ecosystem that then can help other nations around you. That's where you want to be. And we're not your only partners, but I will tell you, being able to work in similar time zones is incredibly useful for actual collaboration, and more than happy to work on it. So, just remind ourselves that the future, the Earth is feeling pretty finite right now, but ultimately the future is our domain, and we're going to use knowledge and our own capabilities to make that future. That's how it's going to happen. If we just let it happen on its own, bad things will happen. So, thank you very much.